Greatness of orthogonal components means why we need independent variable orthogonal components. So that is the discussion that we are pursuing. That is the discussion that we have been pursuing. So that is the science that we are talking about. So if I have a kind of a class and it can be represented through abstract way, but if it has orthogonal components, then can it be completely represented through orthogonal components? That is the idea. Now, rather than having too many variables, too many attributes, a class has attributes, too many attributes, can we make it stand? Can we make it depend upon very few orthogonal components? That is the idea. Like if I have a class and it is a color class. So, and it has now, suppose that it has a kind of 100 colors. Now, I am writing the description of all 100 colors. Rather than I can have so only three variables red, green, and blue. Color is dependent upon three independent variables. Independent in the sense that red is not dependent upon blue and blue is not dependent upon green. So no one is dependent upon each other. If we have orthogonal components and a class is defined represented through all the orthogonal components, then it is maximum in information whereas it is minimum in the space consumption. So that is the science we are talking about. Only thing that is painful is how to find orthogonal components. Like in around, if I see so many colors, then I can keep writing so many colors like yellow or cyan or anything, brinjal color or orange color. So instead of writing yellow and description, I can write 110. Simple. So every possible color in millions and billions of color, I can just write its value in red, green and blue because these three are orthogonal components for the color class. This is the science we are talking about. Now we have seen that if we want abstract class like vector is an abstract class, then the component orthogonal component of vector is x, y, z value because x, y, z are three axes in angular domain where they are orthogonal to each other. 90-degree they are from each other. So no one has any essence of its energy flowing in at 90 degrees. So this is what we have seen. So uh, if you want dot product of these two vectors, then this is what we have seen. Then dot product is if two vectors are in same direction, then multiplication of the magnitude. So we make this as in same direction. So whatever we have, this is vector b cos theta. Now it comes in same direction. Then magnitude of two vectors. So the magnitude of b has reduced to b cos theta and a. So a into b cos theta is the dot product. But we want in orthogonal component. This is new sign. So when we want in orthogonal component, rather than full vector, we place along the another vector. Now we'll take these two vectors components along x-axis, y-axis, z-axis because both vector A, B have components along x-axis, y-axis, and means they have presence along x-axis, y-axis, or z-axis. Or in other term, we can say that if there are three vectors, like if there is a vector called A, then it has three components A1, A2, A3. Then if there are three vectors, one going in x direction with a strength A1, one is going in y direction with a strength A2, one is going in z direction vertically with a strength A3. If three vectors they combine together at origin, wherever they go, that vector will have component a1, a2, a3. So now b1, b vector has component a b1, b2, b3. A have vector has component a1, a2, a3. So dot product we can settle with this component. So this is what we saw. Same thing we saw in the cross product. If I want cross product of two vectors, then vector must be orthogonal to each other. Must. Then multiplication of their magnitude is the cross product. So if this vector is b and this is a, then a into b. If they are orthogonal to each other. If they are not orthogonal to each other, then we'll make it orthogonal to each other. So if it is b, then b sine theta. Now whatever their power is, vector is nothing but energy which has direction and power, strength. Now the b's strength is reduced to b sine theta. B sine theta into A is the cross product. But idea is to find the cross product through orthogonal component. So B1, B2, B3 are the component of B and A1, A2, A3 are the component of A. Now we have to find cross product of each component of A and B with each component. So that is the idea that we saw. Now we are in phase of doing this magic of orthogonal components in calculus. So calculus, what idea is that so with the dot product we saw that the three components what we get. If we want result in a scalar, then we add it. But in cross product, dot product, we want the end result in a scalar because their vector are in same direction. So whatever the components we get, all three components, we sum it. But whereas in cross product, we need three components separately because the result is a vector. So no need to sum it. Now in calculus, the question is like if I have x axis and y-axis, x-axis, y-axis. If there is a graph, if there is a graph, then its equation, then the graph equation would be function over x and y, where x and y are orthogonal to each other. So can we see this? So in calculus also, in vector, we have if there is a vector called a, then it has three orthogonal components a1, a2, a3. Now, if there is a graph which is function over x and y, then x and y are orthogonal to each other. They are independent. So, orthogonal magic is 100% it is coming in when we have line equation or we have the graph equation. So, orthogonal. So, if I say that my function is defined in terms of x and y, my vector is defined in terms of x and y. My vector is defined in terms of x, y, z. My the graph equation is defined in the term of x, y, z. Then your class has attributes as three orthogonal components, three independent components as x, y, and z. So that is the idea. So orthogonal component is bouncing at calculus level. So if we have x, y, z or x, y as independent variable orthogonal component, then we have function over x, y. So in calculus, if I have a graph of paraboloid, then fxy, the function over xy is x square plus y square. That is a function over xy. If I have a graph of sphere, then fxy square equal to 1 minus x square minus y square, or z square equal to 1 minus x square minus y square. If we come in the graph equation, then it will come as x square plus y square plus z square equal to 1. This is the equation, graph equation of a sphere, or z equal to x square plus y square. Then it will come as paraboloid. So if this is center, from center, paraboloid would come. So that is the idea. You understand paraboloid. So if there is a center, if I draw it along x-axis, it will go as x square. So this is x square, or minus side, this is x square. If you go along y-axis, it is again y square. Slowly it will go and it will go that y square. Now if I make, it is a paraboloid. So z equal to x square plus y square. This is the equation of paraboloid. Now question is that I know that my graph equation is dependent upon two independent orthogonal components. Orthogonal component in the sense that x is independent, I know, but x and y, they are independent variable in the sense in no way they have any relations. What is relationship? If I modify x, then there is no modification seen in y. If I modify y, then there is no change in seen in x. But since fxy is function over xy, z equal to fxy, so if I change x, then there is change seen in z. If I change y or either of them or both of them, then there is a change that is seen in z. That is z equal to x square plus y square. So z is dependent component, whereas x, y are independent component. That is the idea. Now I want dz by dx in the sense that how much z would vary in direction of x-axis. In direction of x-axis means if I make a unit change, if I see unit change, okay, if I see change along x-axis, then z is varying. This is what we are talking. If we make variation in independent component, then dependent component changes. So z equal to x square plus y square at any y. At any y means at if we make y constant, y equal to 0, y equal to 1, y equal to 2, y equal to minus 1. At any fixed y, if I vary x, then z would vary. How much it would vary? That is dz by dx. So if at any particular y, if I change x unit, one unit change in x would bring how much change in z. So if it is x-axis, then along z-axis, if it is x-axis, then along x-axis, what is the rate of change that is seen in z? D is dx by dx. Or if there are 2 points, if I take x1 and x2 corresponding to 2 point x1, x2 at any fixed y, where y is fixed. So point is x1y, x2y. So if there are 2 point x1y, x2y, then what is value of z1 and z2? z2 minus z1 divided by x2 minus x1. Delta z by delta x is, if delta x tends to 0, then it is dz by dx. So per unit change along x-axis with a fixed y, how much unit of change it brings in z, that is dz by dx. Per unit change along y-axis when x at particular x, how much change happens in z, that is dz by dy, okay, at a particular x. Now if I know dz by dx, if I know dz by dy, because I know the variation of z along x-axis, variation of z along y-axis. So two components in the variation, two components in the equation z equal to x square plus y square. So two independent variables, two different orthogonal axes, x and y. Then along the x-axis variation, how much z would vary. Along y-axis variation, how much y would vary. So I do. Okay, now question that is arising. Okay, so question that is arising now is that if this is x and this is y, then if this is u, this is any vector that is u. If this is any vector that is u, if I make it like this, it becomes x-axis. If I make it like this, then it becomes y-axis. Then what is the variation? If I make change of unit u for one unit change along u direction, any vector u, how much z would change. So rather what I can say, if there is a point called AB, if there is a point called AB, there is another point called A2B2. Then for at AB, there is a value of z is z. At value of A2B2, the value of z is z2. z2 minus z divided by a2 minus a1, b2 minus b1. Whatever the, through Pythagoras, whatever the distance comes. So delta z by delta u. So delta u is a distance where two points are a, b, a2, b2. For ab, the z value is ab means xy. The z value in fxy function z equal to x square plus y square. So z will have value called a square plus b square. Whereas at a2, b2, z will have value a2 square plus b2 square. z2 minus z divided by a2 minus a1, b2 minus b means a2 minus a whole square plus b2 minus b whole square root. So whatever the z2 minus, this is dz delta z by delta u. Delta u. So along u vector, I have taken a strip of length delta u. So d delta z by delta u. If delta u tends to 0, then dz by du we want to calculate. So we calculated variation of z along x-axis, that is dz by dx. We calculated the variation of z along y-axis, that is dz by dy. Then along any vector x, vector y, vector I, vector j, then along any vector u, what is the variation that is seen in z with unit variation that we take along u vector? That is the question. Now, if we remember the solutions, first we started with this. Anyway, we can calculate if we want dz by du, delta z by delta u, then delta is f a. Okay, the second point is fa plus delta ux. The delta u is the strip size if we have taken, then it's x component. So a plus delta ux comma b plus delta u function over it. So fa delta ux b delta uy minus fab divided by delta u, that is delta z by delta u. So that is what we have calculated. We can calculate it at any point a and b. When we know delta u, then delta u, then ux and uy we can calculate. Now, if we want in kind of equation rather than at keep changing a and b and then calculate fa plus ux, b plus uy minus ab divided by delta u, then it is this is not what we want. We want through equation. Then we came to a linear localization. So at any point a and b, if I have a surface at any point a and b, I calculate the tangential surface. That is called linear localization. Okay, linear localization, local or local linearity. Okay, so local linearity. So local linearity means tangential surface. If I have equation of tangential surface, that is fxy equal to m1x plus m2x, where m1 is a partial derivative along x-axis, that is what we saw dz by dx, and m2 is partial derivative along y-axis. So so fxy, the tangential surface equation at any point a and b, fxy is dz by dx x plus dz by dy y. Now, if we have this equation, then we kind of we put that at a comma v, and then we migrated little bit delta x and delta y. This, if you have delta u, for that delta u we have delta ux and delta uy. In that sense, we have fxy equal to dy by dz by dx delta ux plus dz by dy delta uy. This is what we saw. So delta z by delta, this is same as the dot product of two vectors. This is what we have seen also. Dot product of two vectors, nothing but the multiplication of each orthogonal component, then we have to add it. So dz by dx delta x. So dz by dx and dz by dy is one vector, and delta x delta y are another vector. Now, if we make component wise multiplication, then it is dot product of two vectors, where dz by dx and dz by dy component is a vector component of a gradient vector, whereas u delta ux and delta uy are the component of vector u. So again the question is that can we do rather than, so this is what we did through local linearity. Later we moved on to chain rule. So in chain rule, if I want dfxy by du, then dfxy in the by dx into dx by du. So x component plus dfxy by dy into dy by du. Or if you want, if you know, so here the x component, use x component. Suppose u, so u is dependent, x is dependent upon u is dependent upon t, then dz by dt equal to dfx y by dx into dx by du into du by dt plus dfx by dy by du by dt. So this is chain rule. Whoever is dependent upon other, then we keep proceeding in a chain rule. Now we have come to orthogonal component. So that is the concept. So orthogonal component in the sense that if I want dfxy by du, dfxy by du, dz by du, then rather than going as a whole for z, now will dz by du. So as a whole, that we go for kind of full u. Okay, so we will put u in orthogonal component. So u dz is one, means z, there are three orthogonal component x, y and z. So we want dz by du, but u is a vector and it is not orthogonal component. Z is orthogonal component, but u is not orthogonal component. Here is a trick. Dz by dx, both are orthogonal component. Means z axis and x axis. Dz by du, dz by dx, dz by dy, dz by du. So what is variation that is seen in graph z? Vertical value when there is a along any vector u, that is the question. But u is a vector and it has three components, x, y, z. If it is in xy plane, if u is in xy plane, then it has two component x and y orthogonal. So rather than doing computation through u, we will do computation through its orthogonal component. So first, the u has orthogonal component as x, u has orthogonal component as y. So let's calculate it for x and y. If we want a scalar value, we will add it. If we want a vector value, then anyway these two are the components. So this is the way. These things are not available in any book. I am reiterating. Whatever we are presenting, it is not available in the any book. So our idea is to bring a disclosure on each topic that we are talking about. So that is the scenario. Now dz by du. So going for dz by du, I would say dz by dux along x-axis. Okay, one component. Other component is dz by duy. We'll break now ux and uy, two orthogonal components. Rather than doing computation through u, delta u, we will do computation through delta ux, delta uy. Okay, so what we are trying now? So if I say I want delta z by delta u or dz by du, then delta z by delta ux, one component, delta z by delta uy, another component. Now delta z by delta ux, it is same as we are trying to calculate z along x-axis, nothing more than that. Delta z by delta uy is we are trying to calculate, come up with a value that is function over y, that is there, a partial derivative along y-axis only. So dz by dux is dz by dx as far as equation is concerned. Dz by dy is dz by duy is dz by dy only, because direction is same. Only thing different is magnitude. Okay. Now, if I say dz, if this is the delta u along u vector, if this is delta u, if it is delta u, then delta u has component along delta u, then it has component along x-axis, it has component along y-axis. Okay. So delta ux, delta uy. Now, suppose that delta u is for a unit vector u. U is not a unit vector, but I consider u as unit vector. If that is true, then for okay, so if u is unit vector, first I'll suppose u is a unit vector. Later we'll go if u is not a unit vector. Suppose u is a unit vector. The way I and j are unit vector. Calculating unit vector is not tough job. If I want u to be unit vector, then each component of u should be divided by the magnitude of the vector. So u has component u1, u2, u3 or ux, uy, uz. Then I have to divide ux, uy, uz with the ux square plus uy square plus uz square root, or u1 square plus u2 square, u3 square root. So u1 by u1 square plus u2 square plus u3 square root, u2 by u1 square, u2 square, u3 square root, u3 by u1 square, u2 square, u3 square root. If now the u1 becomes u1 by u1 square, u2 square, u3 square by square root. Now this is the component of a unit vector. Okay. Now we are calculating dz by du. Means if there is a unit change along u vector, then how much unit change we see along z axis. But now since u has component along x, y, z orthogonal component, we will calculate for orthogonal component separately. This is the idea. So dz by dux means dz by dx. So per unit change along x-axis brings how many unit change along z-axis, that is dz by dx. But it is not one unit now. Okay, one unit is along u vector. The one unit along u vector becomes here as u1 by u1 square plus u2 square plus u3 square root, or ux by ux square plus uy square plus uz square root. It is reduced. The magnitude is reduced. The u vector has x component, whereas x component is ux by ux square plus uy square plus uz square root. It is less than ux. So if I calculate dz by dx, that is the direction, into ux by ux square plus uy square plus uz square root. That is the magnitude. So per unit change along x-axis, per unit change, if there is one unit change along x-axis, it brings dz by dx unit change along z-axis. This is what we have seen. That is called partial derivative. So if there is one unit change dz by dx, if there is one unit change along x-axis brings dz by dx unit change along z-axis, then ux by ux square plus uy square plus uz square root unit of change would bring how much unit of change along z-axis. Now the one unit is not one unit now. The one unit is along u vector. U vector's one unit becomes less along x-axis. Or if u is a unit vector, then its x is 1 by 1 square plus 1. X is its whatever the what the so its x component will be less. Okay, so x component will be in a way that if we do square of x, y and z and a square root, it will become 1. So that is the concept. So ux square plus uy square plus uz square root equal to 1. Means ux is 1 minus uy square minus uz square root. If u is a unit vector, then its component, orthogonal component x is 1 minus ux square minus 1 minus uy square minus uz square root, because ux square plus uy square plus uz square root is 1. That is unit vector. If u is unit vector, then its x component is 1 minus uy square minus uz square root. Now, if I say I know dz by dx, I know the variation of z along x-axis. That is nothing but dz by dx. If you know that, it means that per unit change along x-axis brings dz by dx unit change. Now, it is not per unit because u vectors x component, if u vector is a unit vector, then, or if I want one unit change along x-axis along u vector direction, if one unit of change along u vector direction, if I want to calculate, that one unit will turn into 1 minus uy square minus uz square root, that is its x component. That much we want. So if u is unit vector, that is the scenario. If u is not unit vector, then we have to convert it to unit vector. So now the dz by du, that is x component is dz by dux, y component is dz by duy. So x component dz by dux is the x component what we are talking now. That is variation of dz along x-axis, that is the direction. So if there is one unit change along x-axis would bring how much unit of change along z-axis, but that is not one unit. One unit is along u direction. That one unit of u direction will have x component, y component and z component. If I want one unit along u direction where u is not a unit vector, then it will along the x axis it will come as ux by ux square plus uy square plus uz square root. Okay, so fx means partial derivative along x-axis. So fxxy or dz by dx, fxxy into ux by the magnitude of u. So that is the component of the ux plus, now it is a scalar, so we will add the y component plus fyxy into uy by the magnitude of the u, that is ux square plus uy square plus uz square root. So that is its x component and y component. So simple. Means if I want dz by du, then I have to calculate its orthogonal component vector separately. If I want orthogonal components, then it is x direction, y direction. In x direction, we already know dz by dx. If we already know dz by dx, then dz by dx is per unit change in along x-axis brings how many unit of change in z-axis. But here it is not per unit, because per unit we want along u direction. So that per unit becomes how many unit along x-axis, that is less than that. Means delta u cos theta. In plain English, delta u cos theta means if this is the vector, then along x-axis it is delta u cos theta, delta u y theta, delta u sin theta. Okay, or the x component whatever or if there is a vector uxi plus uyz plus uxi, if u is in term of uxi uyj and uzk, then ux by ux square plus uy square plus uz, that is normalized form. So that is less than 1. Okay, so the strength of u vector is ux square plus uy square plus uz square root. If that is the strength and ux is the component, then ux by the strength is that much unit, it will be in x direction. If per unit change along x direction brings dz by dx, then that much unit of change will bring how much change in the dz. That will come as less. If one change brings this much change, then less than one change will bring this much change. So dz by dx into ux by ux square plus uy square plus uz square root. This is x component. Y component is du by dy, sorry, dz by dy into uy by uy square plus ux square plus uz square. So just see that in one go through the orthogonal component we can find the derivative of a 3D surface along any vector. We don't need local linearity, we don't need any chain rule, nothing is it. Just calculate along the orthogonal components, the direction, and you see that we have calculated as per one unit change. So if there is one unit change along that vector u what we want, then how much is its presence, its essence in xy direction. That means, so that you have to multiply. That's it. First get the direction and multiply the magnitude, that is less than 1. Now, if I have equation called z equal to x square plus y square, that is paraboloid. If I bring in 3D equation, that will come as x square plus y square minus z equal to 0. Okay. If that is the case, then we can consider the third also. So this is the way we can grow in the orthogonality, we can say dimension. Now initial phase we had y fx equal to y equal to x square. So y equal to x square. Now along any vector u, what is its component on its x side? That's it. So if I know dy by dx, then dy by dy by du is dy by dx into ux, whatever its component is along the x-axis. That is, that we can calculate. Okay. So that is the concept. So it will be less. Means if u vector has theta angle with x-axis, then u cos theta. Then you can calculate with the orthogonal component. So dy by du equal to dy by dx, that gives me direction into the u's component along x-axis. Okay. In 3D, we saw dz by du equal to dz by dx, that gives me direction, and then use component along x-axis, because per unit change along x-axis we calculated per unit of change in z direction, that is dz by dx, and then per unit is changing now, because we don't want per unit, less than that, because in u direction we want per unit, its component along x-axis and y-axis is less than 1. So, so the dz by du will be less than dz by dx. But we have to add dz by dux and dz by duy. Now we have a new term, dz by du is dz by dux plus dz by duy. This is pretty new. You won't find anywhere else. So this is the magic we saw while calculating the dot product, cross product. Now calculating the derivative of any 3D surface along any vector u. Just calculate pre-computed partial derivative along x-axis, y-axis, and see the essence of that vector along x-axis and y-axis or z-axis if you have the surface equation in xyz. That's it. So nice. So I mean, we'll file a disclosure on it. So be happy and try with your pen and paper.